Welcome all. Today's topic is system models, and in system models we'll be focusing on fundamental models. I'm Sri Devi, Assistant Professor, Department of CSC, RSET. So, one of the system models of distributed computing system is fundamental models. Before knowing more about fundamental models, what do you mean by a system model? What is the need of creating a system model for a distributed computing system? Using such system models, the properties and design issues of distributed systems can be captured and discussed through the use of these models. So each type of such models, each division of each classification of system model is intended to provide an abstract and consistent description of a relevant aspect of a distributed system design. And there are basically three types of system models: physical model, architectural model, and fundamental models. So system models basically ask more questions, or some of the questions it can ask is, what are the entities of the distributed computing system? How do these entities interact? What are the assumptions you make? Or what are the things which your system is intended to do and not intended to do? All such questions will be answered by system models. So now coming to the third type of system model, that is fundamental models. These fundamental models, they will be giving you three different types of aspects. Fundamental models is further divided into interaction model, failure model, and security model. So in this interaction model will actually give you the structure and sequencing of the communication between the elements of the system. There are different entities participating for a distributed computing system, and this interaction model will consider all the structure and the sequencing of the communication between the elements of the system. And another type is failure models, and that will be considering the ways in which the system may fail to operate correctly. And security models, as you all know, like how the system is protected against attempts to interfere with its current operation or to steal its data. Now, why do you need to know these things? Why do you need to make a model? It is, what is the need of knowing what our systems or designs do and do not depend on? Will allow us to decide whether your design will work if we try to implement in a particular system. How? Because we can actually, we need to ask whether our assumptions hold in that system or not. So using all these models, we are actually trying to make explicit assumptions about the system we are modeling. So if we have some assumptions, and if we want to check whether our design, our system will be implemented in a particular system, whether it will be successful in a particular environment, what we have to do is, we have to decide whether the system will work if we try to implement in a particular system. We just ask that system, we just ask whether our assumption is holding in that particular environment or system. That's the importance of fundamental models. So let's come to the first type of fundamental models, that is interaction model. We already discussed that the interaction model can be the interaction between the various entities of a distributed computing system using the communication channels. So taking as the abstract view of this distributed computing system, you can take it as a network of processes. A single process may be working or may be parallelly working in more than one system. That's why I'm saying it's an abstract view. Take it as an abstract view, so that each process, even though it's working in multiple systems, you can take it as a single entity. And this entire thing is actually a network of such processes. You're implementing something using your distributed computing system by the network of different processes, whether each processes will be doing a particular task, is intended for a particular task, and such process will be interacting with each other, and that will be making a distributed computing system. So in this figure, each node is nothing but the processes, and the edges are the communication channels. Now in the interaction model, you have the process even can interact in complex ways. Like, each there are different types of servers involved. Not only the channels, or not only the terminals from which the user is logging into your system. There are different entities in a distributed computing system. You may have simple terminals, um, through which the user is logging in, and there could be mini computers, or any the computers which act as the server, which the server process is running. So within the server process computers, like multiple server process, even they can cooperate with one another to provide a service. Altogether, they can make a new service. For example, take the case of domain name service. So in the domain name service, in the DNS, which partitions and replicates the data at servers throughout the internet. So the various servers will be replicating or partitioning the data, and it will be distributed throughout many servers throughout the internet. And this is actually the multiple servers process is actually trying to cooperate with one another to provide a common service, which is the domain name system. Another example, you can take Sun's network information service. They will be keeping the replicated copies of the password files at several servers in the local area network. And another complex way of interaction among processes is like a set of peer processes may cooperate with one another to achieve a common goal. For example, if you take the case of a video conferencing system that distributes the streams of audio data in a similar manner, but with a strict real-time constraint. So direct peer-to-peer processing is happening in a real-time with real-time constraints. So when these processes are interacting with each other, it involves two things, or it involves two factors which affect this entire interaction. The first one is the communication. The second one is the coordination. How well the communication channel performs. What's the bandwidth? What's the jitter? So all these things we'll be explaining in the coming slides. Now we will be seeing first, how do you measure the performance of a communication channel? How will you model your communication channel for the interaction model? Various terms you need to familiarize here. The first one, the performance of the communication channel is based on is latency. So in this latency, it is a sum of three different times. When something is to be taken by the operating system, that executable program or that process should wait there in the queue. And from there, depending on a particular scheduling policy, it can be like first comes, first serve, or any type of scheduling policies. The operating system will be picking up a particular process from the queue, and that will get processed. So it takes some time for that queuing part. So that is a queuing time. And once the OS has taken it, there is a delay involved. Then the OS is giving that data to the network. So that is the transmission time. Now it was first in the queue. The OS has picked up from the queue, and now it has to given it to the network for passing it to the communication through the communication channel. So that is the transmission time for the first bit of that particular message to reach to the communication channel. So that is the transmission time. Then you have the propagation time. Once it is there in the communication channel, for how much time it takes to reach the destination. So altogether, we can say how much time it takes for a message from point A to point B, that can be termed as latency. So in the figure, you will understand it more better. So here, this is the messages, and you have a queue here. From this, OS will be picking up one. There it will take a queuing time, and then for this to be given it to the network. So this is a communication channel in a cylindrical shape. So here how much time it takes, and then the transmission. After the transmission, we have to propagate that particular message to the destination. So altogether we term it as latency. The second term with which actually helps us to measure the performance of the communication channel is bandwidth. Bandwidth is the amount of data that can be transmitted per unit time. For example, if you say that 10 Mbps, 10 million bits per second. So this is in a second, 10 million bits will be transmitted. So when there is a large number of communication networks are involved, then for the same through the same communication channel, then they have to share the bandwidth. You might have studied about all the multiplexing techniques in order to share a particular bandwidth among multiple communication networks. Then the third one is jitter. It is a variation in the latency on a packet flow between two systems. So for first time, maybe the packet is taking this much time, say time t1. The second time it may take t2. So there is a variation in the latency. So that variation is termed as jitter. So we have seen how do you do or model the performance of a communication channel. The second one we have to consider for the interaction model is how do you synchronize it? It is actually the interaction between two processes. How do you synchronize this interaction? Or how do you order that events? And process is nothing but it is a sequence of events. In a process, first event 1 occurs, it has some effect, then after that event 2 occurs. So it is actually a sequence of events. So in a distributed system, if you have to do the synchronization, there are two options. One is we are making strong assumptions of time. Like we are making assumptions that it will take this much time for the process to complete, or this much time for the message to complete or to complete its journey from the source to destination. It's a strong bound on the time. If you do that, that type of distributed systems are called synchronous distributed system. And if you don't make any such assumptions about the time, it is called asynchronous distributed system. So for which all bounds we have to define for an asynchronous distributed system. It is the time to execute each step of the process. It will be having a lower and upper bound. The process is not executing between this lower and upper bound. It will be taking it as a failure. It will be taking it as an error in synchronous distributed system. And each message transmitted over the channel is received within a known bounded time. Each process has a local clock whose drift rate from the real time has a known bound. What do you mean by this drift rate? We'll be seeing in the next slide. Asynchronous distributed system, so no bounds for the following things. The same list which we applied for synchronous distributed system. So why it is more important is, why do you need that event ordering and synchronization among processes? Suppose you have a node A and node B participating here, and it is there is a common resource, that one which node A and node B is trying to access. Now node A has made a request at 10 a.m. and node B has made a request at 10:02 a.m. But there is a problem, like they are using individual clocks. 10 a.m. is the time shown on the local clock of node A, and 10:02 a.m. is the time shown on node B. But are individual clock accurate and precise? Or one clock might run faster or slower. We need to consider that scenario as well. So all these things shows the importance of synchronization and event ordering in distributed computing system. So what do you mean by this drifting of clock? How a internal clock works? There is a quartz crystal which is oscillating in well-defined frequency, and these oscillations are counted in a register. So when it is oscillating and it has reached a particular count, an interrupt will be generated, and that interrupt is nothing but the clock tick. So at each such clock tick, your computer clock will be incremented by the software. So that's how your local clock, internal clock works. But the problem here is crystals cannot be tuned very perfectly. Your temperature or any external factors can influence their frequency. So the computer clock differs from the real time. There will be a clock drift. And two different systems will be using two crystals, and you know that two crystals will never be identical. That means that oscillations won't be the same for both crystals. So there again there is a chance for a clock drift. That's a clock skew. So the computer clocks on different processors of the distributed system can show different time. So clock drift is the computer clock differing from the real time, and clock skew is the difference in the time shown by two different processes of the distributed system. So both of these things may give you a wrong ordering of events. What could be the solution for this? There is something called universal coordinated time, the time standard. And this 24-hour time standard is kept using a highly precise atomic clocks combined with the Earth's rotation. So there is very less chance for a clock drift. Like it can very rarely go differ from the original time. So this UTC, after this, it can be broadcasted through shortwave radio and satellites. And this UTC is used in many internet and World Wide Web standards. So how do you transmit or broadcast this UTC? It's like there's a protocol called Network Time Protocol, and it's basically designed to synchronize the clocks of the computers over the internet. So they will be transmitting the time information from the UTC system. It's the most used clock synchronization solution, and it's a layered client server architecture based on the UDP message passing. Now, is it enough to synchronize the physical clock? You said that we will be taking up the data from UTC, which has a very good accuracy, and that will be broadcasted using network time protocol. But is it enough? The problem may arise is the value received from this UTC receiver is only accurate to within 0.1 to 10 milliseconds. So at best you can synchronize the clock to within 10 to 30 milliseconds of each other. You have to synchronize frequently to avoid the local clock drift. These are some of the problems faced here. Now the event ordering. Event ordering, there is a solution for all this. There is something called event ordering, and event ordering can be done by a Lamport algorithm. There is a Lamport timestamps and vector clocks. The basic idea here is what usually matters or what is more interest is not that all process should agree on exactly what time it is. That is not the case. But rather, they should agree on the order in which their events occur. There should be a clarity in whether a particular event has occurred before or after an event which is coming from a different process in a different processor. Whether we can keep that track of that order of events, then it is fine. So it is an internal consistency of the clocks that matters, not whether they are particularly close to the real time. But internally, these clocks should be consistent. Let's see how we do. A process in it's a sequence of totally ordered events. That's for any event A and B in process. Either A comes before B or B comes before A. And it's a set of distinct and spatially separated processes that communicate by sending messages to each other. So you should find a way how you can order these events which belongs to multiple processes. There is a term here like happens before. So this algorithm was Lamport algorithm was given by Leslie Lamport in the 70s, and he defined a logical relation happens before among the events. Suppose it is actually the happen before relation on the set of events in a distributed system. It's the smallest relation satisfying these three conditions. If A and B are two events in the same process and A comes before B, then A, that particular sign stands for happens before. A happens before B. This is the case with A and B are two events in the same process. And if A denotes the sending of a process and B is the receipt of that message, then A should happen before B, obviously. And if A happens before B and B happens before C, then A should definitely happen before C. These are some of the notions which we take for a happen before relation. Now let's see what is this Lamport's algorithm and how it helps to make the ordering of events among multiple processes. Now in the figure, there are three types of processes, P1, P2 and P3. And all processes are using a counter or clock with initial value of 0. Make all process use a counter with initial value of 0. There are no local clocks involved. All they have is a counter with initial value of 0. Now, a process increments its counter when a send or an instruction happen at it. The counter is assigned to the event as its timestamp. So here P1, P2, P3, and in P1 you can see there are two events, A which is happening before B. In P2 you have C and D as events. In P3 you have E and F as events. And in the first P1 case, first every process, it will have an initial value, a counter with initial value of 0. The sent event will carry this timestamp. I told you that each event is associated with a timestamp. So the sent event which will carry its timestamp along with them. And for a receive message event, which could be in a different processor, how that counter will be taken updated. That counter is updated by max of local clock and message timestamp plus 1. Whichever is the maximum among local clock or message timestamp, that will be taken and a 1 will be added to it. So here A, B. So from B it is taking to the C, it is sending something, and P2 is receiving that. After some time, it is sending another thing D for P3, and a new event has occurred here. namely F. Let's see it in more detail. Here, there are 4 processes, and as per the Lamport's algorithm, all the counters of each process will be initialized to 0. So P1, P2, P3 and P4, you can see all processes counters are initialized to 0. Now which event occurs first? An event in process P1 is happened first. That's a send message. So that has invoked another event in P2. So while sending, what you have to do is you need to go for the next one. Next counter value will be incremented. So that is 1 here, indicating that some send event has occurred. Now after that, it is coming here. In the receive side, what is the case? It will be taking the maximum of its own counter. What is its own counter? P2's counter is having a value of 0. And what is the event timestamp associated with the incoming event message? That is 1, which is maximum in this, it is 1. So that 1 plus 1, so it will be 2. So that 2 will be taken and given. So that's how it has become 2. Now, after that, there is 3. So when another send event for P2, so when you are sending that, your 2, the present value of 2, that will be incremented by 1 again and it will become 3. Okay, so that 3, that will be given here. How do you calculate? How do you get it as 5 here? Because it will be picking up whenever there is a receive event. It is a receive event. Here, this is also a receive event. Here also it's a receive event. So here and receive event comes. For a receive event, how much timestamp we should give by the local counter will be calculated by a definition. Maximum of local counter and the incoming counter value plus 1. So what is the incoming value? It is 3. And what is the local counter value? It is 4. Which is maximum? It is 4. Then with that 4, we will be adding 1 to it so that it will become 5. So similarly, it happens for all the other cases. Now, this is a corrected example. There was a problem in the previous thing. So here 3 and 5, this is fine. But 5, 6 and 7, here it is 8. Now coming to failure models of fundamental models. There are 3 categories of failures which can occur in a distributed computing system model. That is omission failures, Byzantine or arbitrary failures, and timing failures. Omission failures, with regards to the process, we have process omission failure and communication omission failure. In process omission failure, there are 2 types: process crash and process fail stop. So inside the process crash, the main omission failure of a process is to crash. That is, the process has halted and it will not execute anymore. That's a failure called process crash. And we call it as a process crash if other process may or may not be able to detect the state. If other process may detect, then it is called a process fail stop. But for a process crash, it may or may not be able to detect. And this process crash is detected via timeouts. That means if you are not receiving a message or response from a particular process for a given time, we have a timeout there and it can be detected like that. But that's the case with a synchronous system. We said in a synchronous system, there will be a bound on everything happening in your distributed counting system. There will be a time bound. So there is a time bound on the response of a particular process, and if it doesn't happen, then it is that crash is detected. But what about the asynchronous system? There could be a timeout, but it can only indicate that that process is not responding. It may have crashed, or it may be slow, or the message may not have arrived at, etc. And similarly, so the basic difference between process crash and process fail stop is the other process, whether it's able to detect this particular omission failure or not of the process. Next is the communication omission failure. There are different types of communication omission failures like send omission, receive omission, and channel omission. Send omission is the loss of messages between the sending process and the outgoing message buffer. You know that if there is a process P, there will be an outgoing message buffer before it's moving to the communication channel. And similarly, at the receiving end, there will be another one, like there will be a incoming message buffer which will be taken by the process Q. And so this send omission happens when the loss of the messages between sending process and the outgoing message buffer. In between that, the message has been lost. And receive omission is the message is lost between the incoming message buffer and the receiving process. Channel omission failure is the loss of message in between the outgoing buffer and the incoming buffer. That is, it had lost somewhere in the communication channel. So for a channel omission failure, the loss of the message is between the outgoing buffer and the incoming buffer. It's lost somewhere in the communication channel. Now the second type is Byzantine or arbitrary failures. These refer to the cases when a process or a communication channel they fail to perform the actions that it is supposed to do. So a process it continues to run but responds with a wrong value in response to an invocation. It continues to run but it's giving a wrong response. So it might also arbitrarily omit to reply. So this kind of failure is hardest to detect. The process, you can see that it's working. There's no halt or there's no crash, but the result produced or the intended response is not coming. The communication channels can also exhibit this kind of failures. How? It is by delivering corrupted messages. But this type of corrupted messages is very rare to occur because you have different TCPs. If you follow TCP/IP protocol, you know TCP/IP protocol, it uses checksums to detect the corrupted message and use message sequence numbers to detect non-existent or duplicate messages. So let's to summarize this omission failures. Fail stop, crash, send omission, receive omission, and arbitrary can be applied on the process. And the failure which is only applicable is the channel omission failure, which is only applicable for the channel. And rest of them is affecting the process. The description is given. The timing failures, the last one, these are applicable only to synchronous distributed systems, where there is limits or there is a time bound we have set on the process execution time, message delivery time, and clock drift rate. So any of these failures is result in response being unavailable to clients within a specified time interval. If the process fails to give the response within a specified time interval, it's a timing failure from the processor's side. If a particular message hasn't reached the destination within a specified time interval, that's a timing failure from the communication channel side. So, but in asynchronous distributed system, there's no timing failure because there is no time bound assumptions we have set. Can said to occur like because there's no timing guarantees have been made for asynchronous system. There's masking failures. Like how do you mask these failures? A service mask a failure. A service can mask some of its failures by either by hiding it altogether or by converting it into a more acceptable type of failure. For example, these checksums are used to mask the corrupted messages by effectively converting an arbitrary failure into an omission failure. So after checking this checksum value, it is we have found out that it's a corrupted message. So that message won't be delivered to the receiver side. So it's actually an omission failure. Instead of getting a wrong message, it's always better to have a missing messages so that again it can ask for it and do not have to use the data of a wrong message. Then there is a communication omission failures. This can be masked by reliable communication service like which provides validity and integrity type of things. So there are various ways in which the failures can be masked either by hiding it or by converting it into a more acceptable type of failures. So that's all about the different types of fundamental models in distributed computing system. Thank you all.